Okay, welcome back. Today we're going to continue talking about section 3F in the textbook, which was on duality. Okay, so let me just recall what we talked about last time. So recall, if V is a vector space over F, we define a new vector space, the dual space. What was the dual space? The dual space was V prime or V star. It was just defined to be the set of all linear maps from V to the base field F. So you start with a vector space, you take its dual. This is a new vector space, but these vectors, the vectors in this vector space are like functions on V. And we proved that the dimension of the dual space is the same as the dimension of the original vector space because it had a basis of the same length, right? So if you have a basis V1 through Vn, then we have the dual basis to this basis. This thing is in fact a basis of the dual. So it has exactly the same number of elements. Let's call them phi1 up through phi n. Each of these phi's has to be an element of the dual, right? So each of these phi's is a function on V. How is it defined? Phi j of Vk is 1 if j equals k, and 0 if j is not equal to k. Right, so these phi's are all functions from V to F. They're functions on V because once you've defined it on a basis, that determines the entire function. Right, so I've told you exactly what phi j does by telling you what it does to a basis of V. Okay, also, so that's what it meant to take the dual of a vector space. Also, we saw that you could take the dual of a linear map. Right, so if T is a linear map from V to W, then the dual of T, it's denoted T dual. It's a map from the dual of W to the dual of V. Right, so it's like the arrow flipped around when you took the duals. Okay, well, how is this dual map defined? Right, well, the domain is W dual, so the domain consists of a bunch of functions from W to F, phi. What does T dual do? It has to map it naturally to a function from V to F, right? So how do you get a function from V to F from a function from W to F? Well, what you do is you take this function from W to F, that's phi, and then you just compose with the map that you have T from V to W. So if you start with a phi from W to F, you get a map T of phi from V to F. So this map is T dual applied to the map phi. It does in fact give you a map from V to F. Okay, and the first thing that we're going to do today is we're going to try to understand properties of this process of taking the dual of a linear map. What do I mean by this? Well, we know that if you have several different linear maps, you can do operations to those linear maps. So for example, if S and T are both maps from V to W, you know that you can take this sum, and that's also mapped from V to W. Okay, but now you can dualize everything, right? So you take each of S and T, those are duals. I mean, those you can take their duals. Those are going to be maps from W dual to V dual. Same thing, this map S plus T, you could take its dual, also map from W dual to V dual. And you could ask, well, what is the relationship between S dual, T dual, and the dual of S plus T? Are these related in some nice way? Similarly, you can take a linear map, you can scale it, and then you could take the dual of the scaled linear map, right? So you could take T, You can scale it by lambda and you can take its dual. Or you could dualize T, that's a linear map. And then you can scale that linear map, right? So you can either take duals first and then scale, or you can scale first and then take duals. And you could ask, how are these two things related? Okay, the last operation you have for linear maps is, as long as the domain and codomain make sense, you can compose linear maps. Right, so let me do this here. Here, if S is a map from V to W, and T is a map from U to V, then you can get the composition ST, which is a map from U to W. Again, you can now dualize everything. S dual is a map from W dual to V dual. T dual is a map from V dual to U dual. And S of T dual is a map from W dual to U dual. And you could ask, well, how are the maps S dual, T dual, and the dual of ST related? Okay, and the first proposition basically says that this process of taking duals respects these operations. So the following hold. So 1. For all S and T linear maps from V to W, if you take S plus T, that's a new linear map, and you take its dual, that's the same thing as the dual of S plus the dual of T. Right, so the process of like taking duals respects addition. 2, for all scalars lambda and F, and all T in the linear maps from V to W, again, you can scale the map T and then take its dual. That's the same thing as taking the dual of T and then scaling by that scalar lambda. And then 3, for all S maps from V to W and T map from U to V, if you take the dual of the composition, this is T dual composed with S dual. Okay, but notice that the order of the T and the S changed, but it's actually the only way that it could make sense, right? So the point here is that, what's the picture? The picture is you had a map T from U to V and a map S from V to W. Its composition was ST. It's a map from U to W. Now when you dualize everything, the arrows flip, right? So T dual goes from V dual to U dual, and S dual goes from W dual to U dual, and ST dual goes this way. Right, maybe I should, ST dual goes this way. And all this is saying is that ST dual is the composition of the two maps S dual and T dual. But if you're going from W dual to U dual, you have to do S dual first and then T dual. So it's flipped around the order because dualizing flips the arrows. Okay, so in fact, if you were to write something like S dual T dual here, this thing doesn't even make sense in general because the maps don't go to the correct places. Okay, maybe I should cross this out. Okay, so these are really just computations that need to be checked. So let's do the classic thing where I'll check additivity, and then I'll leave it to you to check homogeneity, the scalar multiplication. And then let's also check function composition together. Okay, so let's prove part 1. So suppose that S and T are linear maps from V to W. Okay, then by dualizing, we get maps S dual and T dual. These are linear maps, sorry, from W dual to V dual. How are they defined? For each phi in W dual, S dual of phi, this is supposed to be something in V dual, it's supposed to be mapped from V to F. This is defined by phi of S from V to F. Right? That's just how we defined what the dual map does, right? I guess I didn't write it here, but this is just t of phi. Sorry, phi of t, right? First do t, then do phi. Okay, similarly, t dual of phi, this is phi of t. Again, this is a map from V to F. Okay, so these two linear maps we can add, right? I can add S dual to T dual. So S dual plus T dual. This is again a linear map from W prime, from W dual to V dual. How is it defined? Well, S dual plus T dual applied to a linear map phi. How do you define the sum of two linear maps? You just say, well, you evaluate on each of the summands and then you add the result. Right? So this function is the function given by just phi of S plus phi of T. Again, just to remind you, this is a function from V to F. Okay, so here I've added the dual of S to the dual of T. I'm describing the right-hand side of this equality. Okay. On the other hand, we could also first add S and T as functions and then take their dual. And so this is for the other side. So S plus T, this is a linear map from V to W. Then we get the dual of S plus T. This is a linear map from W dual to V dual. And how is this defined? S plus T dual, what it does to an element of W dual, this is just phi of S plus T. This is a function from V to F. Okay, so I'm trying to show that this equals this as a function from W dual to V dual. How can I show that two functions are equal? I can show that they do the same thing to every element of the domain. Right, so I'm trying to show that this function and this function are the same. But in these displayed lines, I've shown what they do to each element of W dual. So what this function does to W dual is it gives this function, right? When you plug in a phi, you get phi of S plus phi of T. When you plug a phi into this function, you get phi of S plus T. So I just need to check that now these two underlined things in purple are the same function from V to F. We need phi of S plus phi of T to equal phi of S plus T as functions from V to F. Right? Because then the underlined blue things do the same thing to every single phi. Now again, how do you check the two functions are equal? You just need to check that they agree on every element when you plug it in. Right, so now, for every little v in V, we want to understand how these two things are related. Right, well, phi of S plus phi of T applied to V. By definition, this is the sum of two functions applied to V. You just do phi of S to V, and then you do phi of T to V. That's by the definition of the sum of two functions. Maybe we can write it like this to be clear. Okay, but now let's consider the other side. Let's come at this from the other side. If you take phi of S plus T of V, this is defined to be phi of S plus T. Okay, what am I saying? First do S plus T to V, right? So this is phi of, what does S plus T do to V? By the definition of function addition, you have to do phi of S of V plus T of V. But now phi is a linear function because it's in W dual, which means that you can break phi up over the addition. So this is phi of S of V plus phi of T of V. So this is because phi is linear. And now these two things are equal by the definition of the composition. Right? Therefore, the purple underlined functions, they do the same thing to every V in V. That's just what we checked. We just checked that if you take either of the purple underlined functions, they do the same thing to every V in V. And therefore, the blue underlined functions are the same because they do the same thing for every phi in W dual. Okay, so a little bit, I mean, there's a lot of layers here, right? It's like an onion. There's a lot of layers. So you have to think hard about this, but we have just proven part one, which means that you need to prove part two, right? So two, let's leave this as an exercise. But let's just consider part three. This is proof continued. What about part three? So suppose that S goes from U to V, sorry, V to W, and T goes from U to V. That means that ST will go from U to W, right? Just as we mentioned before, which means that S dual, T dual, and ST dual, S dual goes from W dual to V dual, T dual goes from V dual to U dual, and the dual of ST goes from W dual to U dual. Right, so we should at least first note that both T dual composed with S dual is also a map from W dual to U dual. Right, so at least these two functions have the same domain and the same codomain. We need to check, are they equal as maps? So the question is, are these equal as functions? How do you check if two functions are equal? You just need to plug in everything in the domain. Right, so let's let phi be in W dual. I want to check if these two maps do the same thing. Okay, well, if you take ST dual and you plug in phi, the definition of this is that you do phi of the map ST. Again, this is just the definition of what a dual map does to an element phi in W dual. What the dual map does is it just composes. Okay, but function composition, right? This is phi of S of T, and function composition is associative. Right? Now, what is this guy here? This guy is the same thing as T dual of the function phi of S. Again, because the definition of what the dual function does to a functional is it just composes. And this guy on the inside is the same thing as S dual applied to phi. But now this is the composition of T dual and S dual applied to the element phi, which means that this and this are equal. And since that holds for every phi in W dual, it means that this function and this function are equal. So since this holds for all phi in W dual, this shows that the dual of ST is the same thing as T dual composed with S dual. Okay. So our first goal of today, which was to understand how taking duals behaves with respect to addition, scalar multiplication, and function composition, is just that it behaves in basically the nicest possible way. Okay, our second goal of today is to actually try to understand, if you start with a map T, what are the properties of T dual? Right, so now I'm not talking about any operations between linear maps. I'm just saying I start with a linear map, I take its dual. What do I know about this new linear map? In particular, I would like to understand the null space and the range of the linear map. These are two very important properties. So this is on the null space and range of the dual of a linear map. Okay, so again, T here is a map from V to W. T dual, that's a map from W dual to V dual. The question is, what is the null space of T dual? This is going to be some subspace of W dual, right? The null space of T is a subspace of V. The null space of T dual is a subspace of W dual, right? So it's kind of living in not just the dualized place, right? So it's unclear exactly how this should be related to T. It doesn't seem like there's going to be an obvious connection to the null space of T, for example, because the null space of T is in V, but the null space of T dual is in W dual, right? And then what is the range of T dual? And this is going to be a subspace of V dual. Right, so we can't expect something like, oh, you dualize the null space to get the null space of the dual, because it will live in the wrong place. But we will be able to understand what these things are, right? It's just going to be maybe not so intuitive. So in order to understand this question, I need the following definition. Okay, so let's let U be any subset of V. Okay, so here I'm not requiring that U be a subspace. I'm just saying it's any subspace, any subset. Okay, then the annihilator of U, I don't want to underline it, the annihilator of U is, okay, so the notation is U superscript 0, and it's all of the phi's in V dual such that phi of U equals 0 for all U in U. Okay, so notice the annihilator is a subset of functionals on V. It's all the functionals which vanish on every vector in U. Okay, so this is a subset of V dual. I don't know that it's a subspace. Okay, it turns out it will be a subspace. And here I'm not assuming that U is a subspace. So U is a subset, but the annihilator of U will always be a subspace of V dual. This will be true. We'll prove that. But first, let's think about an example. Okay, so let's let U be the subset. It's in fact a subspace, but the subset of P of R consisting of all multiples of x squared. Sorry. So I should ask, what are some things in the annihilator? Some functionals in the annihilator. Okay, so one example is evaluation at 0, right? We said that this was a functional on P of R. This goes from the set of polynomials to R, and all it does is it takes a polynomial and it evaluates it at 0. Okay, but if we take a polynomial that's a multiple of x squared, so it's x squared times some polynomial q, and we plug in 0, we get 0 squared times q0, which is 0. So this functional vanishes on every element of U. So this is an example of something that's in the annihilator of U. Okay, another example, let's call this linear functional phi, where what it does is sends a polynomial p to maybe p prime of 0. It's another perfectly good functional, right? What it does is it takes a polynomial, it differentiates it, and then evaluates at 0. Well, again, if you start with anything in U, right? So everything in U looks like x squared times q for some polynomial q, and you differentiate, this goes to the derivative of x squared q 0, but then you can use the product rule, right? So this thing is the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. And if you evaluate this thing at 0, they both have a factor of x. So if you plug in 0 into this, you again get 0. So every multiple of x squared, if you plug it into this functional, you get 0. So phi is also in the annihilator. Okay, so the annihilator is just a bunch of different linear functionals that vanish on your subset U. Okay, so we'll see some more examples in a second, but let me first prove that this annihilator, no matter what U is always a subspace. So suppose U is just any old subset of V, then the annihilator of U is a subspace of the dual space. Okay, how do you prove this? To prove that something is a subspace, you need to check 3 conditions. You need to check that it contains a 0 vector, that's closed under addition, and it's closed under scalar multiplication. Okay, well, to check that it contains a 0 vector, the first, does the 0 vector live in the annihilator? Well, what is the 0 vector? The 0 vector in V dual is the 0 functional, right? In V dual, the 0 vector equals the 0 functional. The 0 functional being the function on V that sends every vector to 0. That sends every vector to 0, right? That's what the 0 vector is. So the question is that thing in the annihilator? Does it send every U in U to 0? Yeah, it certainly does, because it sends every V in V to 0, so it certainly sends every U to 0. So certainly U vanishes. I mean, for every U in U, the 0 functional applied to U gives you 0. So this means that the 0 functional is in the annihilator. The 0 functional vanishes on U because it actually vanishes everywhere. Okay, now I want to check that the annihilator is closed under addition. So suppose phi and psi are in the annihilator. Okay, as I said before, notice that we always choose letters to help us think about things. So since we really want to make sure that we understand that the elements of the annihilator are in the dual space of V, so we're thinking of them as functions on V, we should use letters that suggest that they're functions. Right? So phi and psi are traditional letters here. Just like V and W are traditional letters for vectors in a vector space. Okay, well, what does it mean to say that they're in the annihilator? Then for all U and U, you know that phi of U equals 0 and psi of U equals 0. That's what it means to say that they're in the annihilator. But this means that for every U and U, if you take phi plus psi and you evaluate it at U, that's the same thing as phi of U plus psi of U. That's by the definition of function addition, or the addition of linear maps. But this is going to be 0 plus 0 because phi and psi are both in the annihilator of U. So this shows that phi plus psi is in the annihilator view. Okay, and as always, the scale multiplication is really the same thing, but easier. Or just as easy, let's say. Okay, so I'll leave that as an exercise. So this says that if you take the annihilator, you always get a subspace of the dual space, even if you just started with just the subset U. Okay, so let's consider another example. Let's consider R5 as our vector space with the standard basis of the 5 standard basis vectors. And then let's take the dual basis, phi 1 through phi 5 of the dual. Now let's take a subset or even a subspace. It doesn't, right? We can take any subset we want. So let's let U be the subspace spanned by E1 and E2. Right, this is AKA the XY plane in R5. What I can ask is, what is the annihilator of the XY plane? Okay, well, certainly we know some things in the dual that return 0 for every element of U. As a note, that certainly phi 3, phi 4, and phi 5 are all in the annihilator of U. Why is this? Because how is phi 3 defined on, well, phi 3 of E1 is 0, and phi 3 of E2 is 0. This is by the definition of the dual basis. By definition of the dual basis, phi 3 is 0 on E1, E2, E4, E5, and it's a 1 on E3. Right? But if phi 3 is 0 when you plug in E1 and when you plug in E2, it's 0 when you plug in every linear combination of E1 and E2. So together, this will imply that phi 3 of V equals 0, or let's say U equals 0 for all U and U. Same for phi 4 and same for phi 5. So at least we have 3 elements, 3 linearly independent elements even of the annihilator. Okay, but the claim is that actually the annihilator is just the span of these 3 dual basis vectors. Okay, well, every element here, right? So let's show this. Let's show both inclusions. So first, let's show that everything in the span is in the annihilator of U. Well, an element of this span, an element here, is equal to C1. Actually, let's use numbering. C3 phi 3 plus C4 phi 4 plus C5 phi 5. I need to show that this element, which is an arbitrary element of the right-hand side, is in the left-hand side. So I need to show that it vanishes on a vector, every vector in U. Okay, but C3 phi 3 plus C4 phi 4 plus C5 phi 5, if you apply it to, let's say, alpha E1 plus beta E2, this is an arbitrary element of U. Since everything is linear, you just get C3 phi 3 of alpha E1 plus C3 phi 3 beta E2 plus C454 alpha E1 plus C454 beta E2 plus C555 alpha E1 plus C555 beta E2. And in fact, since the phi's are linear, you can pull out all the scalars, right? I maybe should have done it actually. But then you just get phi 3 of E1, which is 0, phi 3 of E2, which is 0, right? All of these terms are just 0. So in the end, you get 0, which shows that any linear combination of phi 3, phi 4, phi 5, when you plug in any vector in U, you get 0. So this shows that this element is in the annihilator, which shows the inclusion, this first inclusion that we wanted. So now we have to show that the annihilator is a subset of the span of phi 3, phi 4, and phi 5. How can I show that every function which vanishes on U, you can write as a linear combination of phi 3, phi 4, phi 5? Okay, well, remember the dual basis is a basis of the dual space. So since the phi's are a basis of V dual, every element of V dual can be expressed as sum C1 phi 1 plus C2 phi 2 plus C3 phi 3 plus C4 phi 4 plus C5 phi 5. Now let's suppose that this thing is in the annihilator of U. So suppose that this element is in the annihilator of U. Well then, certainly it has to vanish on E1. My hand is getting tired, but maybe I should have done R4. Right? It vanishes on U, so it has to vanish at E1. But now, since this is the sum of functions, you can just plug the E1 into each function. When you plug the E1 into each function, this will be 0, this will be 0, this will be 0, this will be 0. You'll be left with C1 phi 1 of E1 equals 0. But phi 1 of E1 equals 1, so this says that C1 equals 0. Similarly, when you plug in E2, you'll get that C2 equals 0. Right? Which means that if you take any function in the annihilator of U, this coefficient is 0 and this coefficient is 0, which means that everything in the annihilator of U is definitely in the span of phi 3, phi 4, phi 5. And since we proved both inclusions, this shows that the annihilator of U is exactly the span of phi 3, phi 4, and phi 5. Okay. So we've shown that you take any subset and the annihilator is a subspace. We've shown for every subset U, the annihilator is a subspace. Okay, but what if U is a subspace, as it was in this previous example? Then U is a subspace, and the annihilator of U is a subspace. Right? Of course, one is a subspace of V, and one is a subspace of V dual. But you can still ask, how are they related? Here's the result. So suppose that V is finite dimensional. And U is a subspace. actually a subspace now, then if you take the dimension of U and the dimension of U, the annihilator of U, you get the dimension of V. Which is what happened in the previous example, right? Here, U is a subspace of dimension 2. And we saw that U, the annihilator of U, was a subspace of the dual space of dimension 3. So they added up to 5. This is true in general. So let's prove it. Okay, so the proof goes like this. Let's consider the inclusion map. We'll denote it with an I from U to V. What is the inclusion map? It just takes an element U in U. And since U is a subspace of V, U is also in V. So it just maps U to U. It just includes U into V. Right? You plug in a U in U, and it just spits out U, which is also in V. Okay, this is a linear map. You can check that. Okay, and by taking duals, we know that the dual of the inclusion map is a linear map from V dual to U dual. Okay. Everything in sight is finite dimensional, right? I assume that V is finite dimensional. That means that U is finite dimensional. That means the duals of both of those things are finite dimensional. So we can use the rank nullity theorem. So the rank nullity theorem applied to I dual gives that the dimension of the domain is equal to the dimension of the null space of I dual plus the dimension of the range of I dual. Now we just need to think about what are the null space and the range of I dual. Okay, so what is null of I dual? Okay, well, by definition, I dual, this is a function from V dual to U dual, is defined by I dual of phi is equal to phi of I. So what is the null space? The null space is all of the phi's. This is a set of all of the phi's in V dual such that I dual of phi equals 0. That's just the definition of the null space of a linear map. Well, what does it mean to say that a functional phi in V dual satisfies this property? Well, I is the inclusion. So what I does is it just takes U to U. And then when you apply phi, you get 0. So altogether what this says is that the null space of I dual are exactly the functionals on V where when you plug in something in U, you get 0. This is exactly the set of functionals phi in V such that phi of U equals 0 for all U in U. That's really what this inclusion is doing, right? This inclusion is saying, well, first you start with any vector in U, you consider it as a vector in V, and then you apply phi. So what that's saying is that these are the functionals that when you plug in vectors in U, you get 0. But this is exactly the definition of the annihilator of U. Okay, so the annihilator of U is just the null space of the dual map of the inclusion of U into V. That's really what we've shown here. Okay, so null of I is, of the dual of I is U, the annihilator view, right? So that takes care of this piece. What is range of the of the dual of I? Okay, well, by the definition of dualizing, range of I dual. Okay, what is the definition? Again, the definition is this. This is what I dual does to an element in V dual. So the range looks like all linear functionals that look like the output of this function. So it's all of the psi's in U dual such that psi equals phi of I for some phi in V dual. In other words, the range here consists of all of the maps in U dual that can be extended to a linear functional on V, right? It's all of the maps in U dual such that there's some linear functional on all of V, and these two functionals agree on U. That's what the condition in this set notation says. All of the functionals on U that can be extended to a functional on all of V. But the point is that every linear functional can be extended to a linear functional beyond phi on V. Right? Every linear functional has this property. You basically proved something like this on your last problem set, or problem set 3, I think. You show that if you have a function defined on a subspace, then you can define a function on the whole space by extending the basis. I guess there's a finite dimensional hypothesis. You extend the basis of the subspace to a basis of the whole space. And then you define the function to be the same on the basis of the subspace, but just 0 or whatever you want on the rest of the basis. So you can always extend. I guess I could just give you a number. It was here, problem 3.a.11, which means that the range is actually just all of U dual. So that's the green thing is just U dual. That's this thing. Okay, but remember we also proved that the dual space has the same dimension as the original space. So what we've just shown is that the dimension of V dual equals the dimension of the annihilator view plus the dimension of the dual of U. But since for a finite dimensional vector space it has the same dimension as its dual, we can just ignore these duals. This is the result that we wanted. Okay, so this proof is actually kind of short, right? The hard part is understanding what all the maps mean, what the null space is of a weird dual map from some dual space to another. So there's like some abstraction that needs to take place in your mind, but the actual components of the proof are very straightforward. It's a use of the rank nullity theorem, I guess. And then just understanding the definition of the null space of the dual map and the range of the dual map, which I don't think is easy, right? This is the point I'm trying to make. Okay, our last result for today will completely characterize the null space of the dual map. So here, all we said was that we gave a relationship between the annihilator of a subspace and a subspace. right? But we'll need this to prove the following characterization of the null space of a dual. So let's suppose that T is a linear map from V to W. Then the thing we're interested in is the null space of the dual map. This is exactly the same thing as the annihilator of the range. Remember I was saying that, well, you can't expect it to be related to the null space of T, because the null space of T lives in V and the null space of T dual lives in W dual. But the range of T lives in W. So you might expect some relationship with the range, and it's exactly the annihilator of the range. And if V and W are finite dimensional, then the dimension of the null space of the dual map is the dimension of the null space of T plus the dimension of W minus the dimension of V. Okay, so this is just going to be an application. I mean, this part of the proof is just going to be an application of the rank nullity theorem and the previous result. But let's prove that the null space of the dual is the annihilator of the range. So let's show both inclusions. So let's first show that the null space of the dual is contained in the annihilator of the range. So suppose that phi is in the null space of the dual, which again is a subspace of W dual. Okay, well, what does it mean to be in the null space? It means that T dual applied to phi equals 0. Of course, the definition of T dual of phi is phi of T. Okay, well, to say that this is the 0 functional means that whenever you plug in any vector, you get 0. Right, so to say that this is the 0 functional, right? So I should say that this now is in V dual, right? T dual goes from W dual to V dual. I'm saying when you plug in phi, now you're in V dual, and you're getting the linear functional that's 0 in V dual, right? Maybe it's clear if I put it like this. This 0 is the one in V dual. So to say that this is the 0 functional in V dual says that for all V in V, phi of T of V equals 0. Right, but this means phi of T of V equals 0 for all V in V, which exactly says that phi, if you plug in any element of the range, you get 0. Phi, if you plug in any element of the range, this is what an arbitrary element of the range of T looks like, you get 0. So this says that phi is in the annihilator of the range. Okay, what about the reverse inclusion? Suppose that you have a phi in the annihilator of the range. Again, what this means is that, so for every W in range T, phi of W equals 0. Okay, but every vector in the range can be written as T of V for some V in V, maybe more than one, right? So if W is in the range, this implies that W equals T of V. There exists a V in V such that W equals T of V. This means that for every V in V, since TV is in the range, we get that phi of TV equals 0. This is true for every V in V. right? And this means that T dual of phi of V equals 0 for all V and V. In other words, T dual of phi, this is the 0 functional on V. That means that this is equal to the 0 vector in V dual. And this means that phi is in the null space of the dual map. Okay, so really, I mean, in both directions, it's essentially the same argument. You just write down the definition of being in the null space of T dual. You write down the definition of being in the annihilator of the range of T. And it turns out that they're the exact same condition. It's exactly a condition that phi of T applied to every V gives you 0. Okay, and now I need to prove this equality, this dimension business. So let's do that. So this is continued. Now, if V and W are both finite dimensional, then the dimension of the null space of T dual, we just show that this is the same thing as the dimension of the annihilator of the range, because those two things are the same subspace of W dual. But we showed that if you take the dimension of the annihilator and the dimension of the subspace, right? So we showed that dimension of range. Wait, what did we show? Sorry. We showed that dimension of U plus the dimension of its annihilator equals the dimension of the ambient space. And here the ambient space is W dual. So if you subtract this to the other side, you see that this is the same thing as the dimension of W dual minus the dimension of the range of T. So this is why the result that we just proved. Okay, now what's the dimension of the range of T? By rank nullity, this is the dimension of V minus the dimension of the null space of T. So this is by rank nullity. Okay, but I mean, I erased the dual here. The dimension of W dual is the same thing as the dimension of W, so I can just erase that. And now you just rearrange this to be dimension of the null space of T plus dimension of W minus dimension of V, which is what we wanted. Okay, I think the point here was to try to write down the dimension of the null space of T dual in terms of the dimension of the null space of T. And again, they sort of live in different places, but you can use the rank nullity theorem to understand the difference between those two places. So that's really all this is. Okay, so like I think I've said several times, I think this duality section is probably pretty challenging if you're first learning about dual things. So I'm trying to go slow, but slow here means that we'll spend 2.5 lectures on duality, and then we'll jump into chapter 4. Okay, so we just spent 1.5 lectures on duality. Monday, I'll again talk about duality. And then Wednesday is your midterm. Okay, so your midterm covers up through here. So midterm material ends here, which is to say in the middle of 3F. Okay, so you may be asked to prove something about annihilators or null spaces of dual maps or something, right? Okay, so Monday we'll continue with 3F.